Okay, so I'm going to just go over assignment 3. Um, do people have questions that they want me to start off by answering?
Yeah. Could you go over number 4 first?
Number 4.
Thank you.
Yeah, so uh, for number 4, there's a few different ways that you can go about showing that this is not, or that these guys are not equal. Does anyone have ideas on how? Cool. Both are even permutations. That should do the trick. There are a few other things. You can show that the cardinality of H is going to be strictly less than the cardinality of S4. You can also find some element of S4, such that, so find X in S4 such that X is not in H. Right. So how do people want to go about doing this? So Justin, you suggested they're both even permutations. What does that mean? What does that tell us? Cool. What does it mean that they are even permutations versus odd permutations? Can somebody give me a definition of that? Doesn't have to be Justin. Anybody? Kyle, do you know what that means?
No, I'm trying to find it in the lecture notes right now.
Kuan Yu? Is that how you say it?
Yeah, I have no idea.
No?
Yeah.
Justin's picking on you. Okay, Justin, how about you? Yeah, so an even number of transpositions. So let's just go through and so if we, what's the 2-line notation look like for 1, 4, 3? 1 goes to 4, right? 2 goes to 2. 3 goes to 1, and 4 goes to 3. Right? What about what if we were then to stack this guy with, do we want to compose it with the other guy, or do we want to compose it with itself? let's compose it with itself. What happens if we compose this guy with itself? What do we get? So 4 goes to 3. 1 goes, or 2 goes to 2 still. 3 goes to 4. And 4 goes to 1. Right, and then if we were to compose this guy with itself a third time, then we would get back to the identity, correct? Correct. You don't have to calculate that, right? Because if it's a 3 cycle, then when you complete it 3 times, it's going to get back to the identity. It's going to be the same thing with this guy. This guy is going to have 1, 4, 2. Sorry. 1 goes to 4, 2 goes to 1, 3 stays at 3, and then 4 goes to 2. And then we'll get this, if we extend it again, what would we get? We would get 4 goes to 2. We would get 1 goes to 4. We would get 3 stays at 3. And then we would get 2 goes to 1. And then if we were to compose this again, we would get the identity. So that tells us that anything that we're going to generate off of a mixture of these guys is going to reach the identity in an even number of steps, which tells us that we don't have anything that reaches it if we raise it to an odd power, which is basically what Justin was getting at, I think. Is H cyclic? No, because we need both of these guys to generate H. We can't generate it with either of them, and you can see that based on the fact that we went through the entire cycle for each of them. Does that make sense? Does that make sense? Cool. So I'm going to clear all drawings. Do people have any other requests before I just kind of start going through in order?
I was gonna ask 6.
6. Yeah. I'm not sure. I think H will have 12 elements once you mix them. So, but it's only going to. Yeah, actually. So if I thought it only had 6, what I would have told you guys to do is I would have told you to just straight up make the Cayley table, because that wouldn't take that long. But I'm pretty sure that it's if it's 12, then that is going to take a long time. So we actually listed off at least 4 of the different elements, and then if you mix them, I'm pretty sure you'll get more than 6. But if it's 12 by 12, that's a big Cayley table to do by hand, and I would not expect you to do that. So find an element of a non-trivial automorphism phi of S3, then determine the order of phi, and recall so what is a non-trivial automorphism? I think Marius is giving a specific example. But what is the general concept of what is an automorphism? Lucy, what's an automorphism?
Sorry, I'm blanking right now.
Pedro?
I don't really know.
Okay, let's just do this etymologically, right? What does morphism? What are some other words that we have that have morphism in them? Come on, guys. Homomorphism, right? That is a mapping from one set to another. So morphism is basically about these maps that preserve some type of structure, right? Auto, what's automatic mean? It means that something runs by itself. So an automorphism is a mapping to itself. Does that make sense? The order of phi. So that is a good question. I believe that it is talking about the permutations that you're doing on it. I don't want to give you guys something wrong, so I'm just going to order of automorphism. Make sure that I'm not giving you something wrong here. The cardinality of the underlying set. In the case of an automorphism, the cardinality is the set of all automorphisms, i.e. a particular group. Okay, so it's the number of automorphisms of your group that you're doing. So someone give me an example of an automorphism. So it's we're basically being asked how many different automorphisms are there. Find an example of a non-trivial automorphism. So non-trivial, that just means you're not doing the identity automorphism. So this is basically just asking how many different ways there are for me to permute S3, right? So I'll get an automorphism if I just switch 1 and 2. If I switch 1 and 3, if I switch 2 and 3, if I switch 1 goes to 2, goes to 3, if I switch 1 goes to 3, goes to 2, and then both of these guys loop back. And then if I switch, if I switched what I do 2 switches to 3, switches to 1, 3 switches to, sorry, actually that I believe is all of them, right? Yeah. That's all of them. Because we don't have the identity automorphism. We should get 6, so that's good. Does this make sense? Or does this feel like I just pulled something out of a hat?
So we don't include the identity because it goes to itself.
So it's, I believe that we have to include it in determining the order, but it is not an example of a non-trivial automorphism, because it is the trivial automorphism. Does that make sense?
Yeah.
Cool.
So for the an example of a non-trivial automorphism would be like 1 to 2, something like that.
Yeah.
Okay.
And in fact, that's, yeah. So that recall that for the non-trivial groups S3, n equals h is equal to 2, 3, h is equal to, find the image of the under 5, each of these 4 non-trivial subgroups. Okay, so these are the 3 subgroups. So these are 3 subgroups of S3, right? H1, H2, and H3. And then it's basically just asking you to find the image under phi that each of these would give you. So you pick one of these guys and then generate that under phi. See what you get. Does that make sense? Does that make sense? Yeah, it does feel a little bit. Okay, so somebody pick an automorphism for me to do. Okay. Yeah, I think you're right. I think that, yeah, Marius, that does make sense. So that would be the cardinality. I guess that's a different concept from whatever popped up when I searched this. But the cardinality of phi, that would make sense as an example of the order of it. In which case, this guy, if you were to do phi of phi, you would get back to your original set. So this would be of order 2 versus one of these guys, it would be of order 3. Does that make sense? Do people see when I pull up the chat box? Does that
No.
get shared on the screen?
No, I don't think so.
Okay. So then that might sound strange. I was just reading Marius's comment. I think he's right that that's probably that makes more sense as a relevant concept of order than whatever came up when I searched it. So for order of phi, he's suggesting that that's asking how many times do I have to apply phi to get back to what I originally started with, which would just be in these case. So in this case, 1, 2 would get me back. I would have to apply it twice to get me back to what I originally had. 1, 2, 3. I would have to apply it 3 times to get me back. That I think probably makes more sense as a concept of the order of phi. So recall for non-trivial subgroups. So let's say I pick 1, 3 as my subgroup. Then in this case, I would replace it with dealing with the group 1, 2. So if I switched 1 and 3, then when I do this, I would now be dealing with 2, 1, which we normally write as 1, 2. That group instead. Here, I would actually just get back to, so I would be switching them. So I get 3, 1, which is just itself. Here, I would have 1, 2. If I were to apply this guy, then I would switch the 3 and the 1, right? So we normally write that as 2, 3. So basically, I would just be permuting which subgroup it corresponds to. Does that make sense? Cool. Do people have other specific questions that they want me to go over?
Five.
Okay, so for each of the following choices of n and sigma, determine the number of permutations that commute with sigma. Give a non-trivial, i.e. alpha not equal to sigma example for each. Okay. So, okay. Marius is saying that you guys have a formula for this on the slides. In which case I will do. Marius, do you know which slideshow it is? Okay, cool. Thank you. So for A and D, finding one that's that commutes is going to be super trivial. You just pick something that has elements that don't overlap at all. Otherwise, you'll have to work a little bit harder. But none of these should be terribly difficult to find a non-trivial example of something that commutes with it. Do people have other questions? Three, sorry. Verify that I is not a subgroup of S6. Okay, cool. Cool. So check your formula from the slides for October 23rd. So a 6. Well, what do we know for these guys that so if sigma squared is equal to epsilon, what do we know? Yeah, everything's its own inverse. So what does it look like? Yeah, exactly. Everything looks like either 2 cycles or compositions of 2 cycles. So 1, 3, 2, 4. That's also fine. So must be disjoint though. Yeah, because otherwise it would just be a 3 cycle. Yeah, sorry. Yeah, exactly. Yeah, I mean something that an element that you would write as these double 2 cycles. But what you just suggested is actually the way that we show that this is not a group, right? So if I do 1, 2 composed with 2, 3, what do I get? Well, let's just do the stacking here. So, and we'll just pretend everything else doesn't exist. So 1 goes to 2, which goes to 3. 2 goes to 1, which stays at 1. And then 3 stays at 3, which goes to 2. So then we get 1, 3, 2, which this guy right here is, if we square it, is not equal to the identity. So 3a is, we just show that if I apply the group operations to it, then I can get some element that would not be in the set. So it's not closed, which groups are by definition closed, right? Does that make sense? So list all possible cycles that permutation in I could have. So this is just basically saying, first off, how many just 2 element cycles can we have here? $15, that sounds right. So it would be annotate clear. It would be 6 choose 2, which would be 6 factorial divided by 4 factorial 2 factorial, which would be 15. So that's right for the first set, but then we also have to group in the second one, right? So how are we going to calculate that? So we're allowed 1, 2, 3, 4, but not 1, 2, 2, 3. It's not quite just 2 times 6 choose 2, I don't think, right? Because we have that issue right there. So for each of these elements, so if I have 1, 2, if I have 1, 2, then for the first element, I can choose 4 options, right? And then for the second element, so I have 4 choices. And then for the second, I have 3 choices, right? So that tells me I have 15 times 12 options for the second guy. But then I'm gonna have to divide this by 2, don't I? So divide that guy by 2. Why do I divide that by 2? Anybody? Why do I divide that by 2? So any idea?
Is it because you have 2 of the 2 cycles?
Yeah. So I did 1, 2, and 1, 2, 3, 4, and 3, 4, 1, 2 are the same. So should it be divided by 4? Why is it divisible by 4? Oh yeah, you're right. Divided by 4. Divide that by 4. This guy should be 4 choose 2, which would have already had the division by 2. The big thing is I don't care what order I pick these guys in. So I have 2 reasons to divide by 2. 1, 2, 3, 4 is the same thing as 1, 2, 4, 3 as well. So then you'll get that's equal to 45, I guess. And then you can repeat the process again because you can have triple groups and then just sum them up. But that is the basic idea. Does that make sense? And then so for B, I would just suggest rather than actually listing out everything, I think you can get away with just doing the base cycles, the 1, 2, 1, 3, 1, 4, blah, 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 all the way down to 5, 6, and then say any disjoint combination of these. Because otherwise it gets pretty high. Cool. Other questions? Two. So find 2 different factorizations of this guy as products of transpositions. So how am I supposed to factor this? It's one really obvious way, right? What is the super obvious way?
You can do 1, 3, 1, 2, 4, 7, 4, 6, 4, 5.
Okay, you went with the less obvious way, but that should work. The obvious way is 1, 2, 3, and then 4, 5, 6, 7. Right? Does that make sense? Cool. What is A7? So tell me, somebody give me what your description of A7 is. Michael, describe A7 for me.
Isn't it like the permutation group with 7 elements?
Well, so the S6 is the permutation group, right? Or S7 is the permutation group, right?
Yeah, is A the abelian group?
No, it's a restriction of the permutation group. Lucy, do you know?
No, sorry.
Marius, you got this?
Yeah, I think it can be formed using transpositions, right? Or disjoint transpositions.
Yeah, so the formal definition here. Of so it's A stands for alternating, right? So the alternating group of degree 7 is going to be the AN is the alternating group on n elements. So what does it mean for the alternating group? Well, AN, first off, is always going to be a subgroup of SN, and it is comprised of all the even permutations. So what does that mean? So yeah. So what is even number of Maris, are you asking if I mean even permutations or even number of permutations?
No, I'm asking if that's what the alternating group is. It's just can be formed using an even number of transpositions, right?
Yeah. So it is, yeah, it's the group of all even permutations on S under composition. So yeah, it is the basically yes, yeah. So is this guy an A7? Can it be written in terms of even permutations? So that is your answer. So we've just said it cannot. So other questions for the last 7 minutes? Nothing? Or so I'm gonna stop